Bodhan Satvik and welcome to my channel. Today we are going to deal with Newton's laws of motion. This is one of the most easiest and important topics for IIT-JEE, NEET, BITSAT and other competitive examinations. In our previous chapter kinematics, we have dealt about rest and motion, which are effect of something. That something, that cause is going to be dealt in this lesson. That is nothing but force. Force is the one which causes the change of the state. We can define force as the influence of surroundings. Force is a vector quantity. That means it has both magnitude as well as direction. The units of force are given by Newton and dyne. Newton is SI unit and dyne is CGS unit. We can convert 1 Newton to dyne by this one. 1 Newton is equal to 10 to the power of 5 dyne. Basically, forces are of two types, non-contact forces and contact forces. Examples of non-contact forces are gravitational force, magnetic force, electrostatic force and many. Coming to the contact forces, tension, normal reaction, friction, spring forces, etc. Coming to the non-contact forces, gravitational force. Only gravitational force is going to be dealt in class 11, remaining are dealt in class 12. Gravitational force is exerted on any massive object. It means any particle which has mass. Massive object means any particle which has mass. Gravity is equal to 9.8 meter per second square or 32 feet per second square. Generally, we take it as 10 meter per second square. Now, normal reaction. A surface in contact exerts a normal reaction away from the body, away from the surface in contact. Let us refer these three examples. This is the surface of contact. Away from this contact surface, that is perpendicular. This is perpendicular to this, and this is a circle. Placing a body here, it normal reaction acts perpendicular to surface of contact, that is this. If we place a body here, normal reaction acts on this direction. One point to note here, that all the normal reactions join at the center of the circle, and this is a wedge and a block. The normal reaction exerted by wedge on the block is towards this direction, and normal reaction exerted by the block on the wedge is exactly opposite. Next force, tension. Tension is the pulling force exerted by the string. In this chapter, we are going to take the string as massless and frictionless. Free body diagram. In this free body diagram, we are going to assume a body as a point mass, and we are going to mark all the forces acting on it. Let's take this example. This is a pulley, and this is a string, a massless string, and this pulley is frictionless. This is a block of mass small m, and this is of capital M. This has higher mass. In this case, let's draw the forces for this small m. The forces acting on this are tension away from that and mg towards that is always downward, perpendicular. And tension is same throughout the string if the string is massless. Tension is towards the tension is same in the string if the string is massless. If it has mass, tension varies from point to point. Let's now see the free body diagram of capital M. Tension acts upwards and weight mg acts downward. Coming to the free body diagram of pulley, 2T acts upward and tension T and T acts in either of the direction. Since the pulley is massless, it doesn't have any weight acting. Newton's first law. Newton's first law states that state of a body doesn't change until external force is applied. That implies if F net is 0, that body is in equilibrium. State doesn't change. It means if a body is at rest, until any external force is applied to it, it remains at rest. And a body is in is moving with uniform velocity. Until any external force is applied to that body, it moves with uniform velocity. Newton's second rate of change of momentum is equal to force applied. F equal to delta P by delta T. That is change in momentum by change in time. Let us consider V as final velocity and U as initial velocity. mv minus mu by delta T. You know V minus U by T is nothing but acceleration. That implies F bar is equal to ma bar. Average force is equal to delta P by delta T from this one. But if mass varies, F is not equal to ma. Let us take the example of jet plane and rocket. Fuel keeps on decreasing. That means mass in the rocket keeps on decreasing. Mass varies in this condition. In this condition, we can't use F is equal to ma because mass keeps on varying. And on conveyor belt, velocity is constant, but the particles on the conveyor belt the mass of the particles on the conveyor belt keeps on changing. So this is the correct one. F is equal to m dv by dt plus v dm by dt. This is actual second law. F is equal to ma is not always true, but this is always true. If mass does not change, this is dm by dt is equal to 0. That means m dv by dt. dv by dt is acceleration. F equal to ma if mass does not vary. If mass does not vary, dm by dt is equal to 0. This is the second law. Coming to a few examples, a horizontal force is applied on these three blocks. Then we can find out the acceleration by F by m. Here any mass is not changing by time. So F equal to ma and A is equal to F by m. F by net force by net mass. Considering this whole as a system, acceleration is equal to F by m1 plus m2 plus m3. Considering this example, these are two different strings, so they have different tensions. Let us consider the tension in the lower string as T1 and other as T2. Then T1 and the lower block weight is small m and the upper block mass is capital M. Then T1 is equal to small mg and T2 is equal to small m plus capital M into g. We can prove this. See, consider this one. Drawing FBD for capital M, weight mg will be acting downwards and T2 will be acting upwards, and again T1 will also be acting downwards. That is equal, then as it is in static equilibrium, F net is equal to 0. That means the forces in opposite direction are equal. T2 is equal to T1 plus capital M into G. This is equation number 1. And drawing the FBD of small m, mg will be acting downwards and T1 will be acting upwards. That implies T1 is equal to small m into g. This is equation 2. We got the value of T1. Substituting it in equation number 1, we get T2 is equal to mg plus capital M into g. that is m into m plus m into g. Here we go. Here we got the same results. And another example. Let us consider this angle as alpha and this as beta. These both are two different strings connected to a same block. Then T1 cos alpha plus T2 cos beta are equal, and T1 sin alpha plus T2 sin beta is equal to mg. Here we can prove that one also. If this is the T1 and this is also T1 if the string is massless. Consider the string is massless. Let us divide the tensions in horizontal and vertical components. We get T1 cos alpha in this direction, T1 sin beta, sin alpha, T2 cos alpha in this direction, T2 sin beta in this direction. This is cos beta. Fx is equal to 0 implies T1 cos alpha is equal to T2 cos beta. Here we can see that horizontal forces are only T1 cos alpha and T2 cos beta. And coming to the vertical forces, T1 sin alpha plus T2 sin beta is equal to and another force will be acting here, that is weight mg. Okay, that is equal to mg. Hence proved. If a pulley and two blocks are on either side of the pulley, if one block is going up with the acceleration a, then other would be going down with same acceleration a for a fixed pulley. But if the pulley is moving, acceleration of pulley is equal to acceleration of a plus acceleration of b by 2. Here we must consider the directions also. I'll be doing another video on pulleys and problems of that. Newton's third law. Forces always exist in pairs. That is Newton's third law. Action-reaction pair. We have learned that for every action there would be equal and opposite reaction in 9th and 10th classes. But remember this. Forces always exist in pair. Action and reaction act on different bodies. If I press the paper with the pen, the normal force will be acting on paper and the reaction will be acting on pen on different bodies. They won't act on a same body. For a weighing machine, weight is equal to normal reaction. If we stand on a weighing machine, it does not calculate our weight. It calculates the normal reaction. The normal reaction is equal to mg if we are in rest. These are some cases of normal reaction. If n is equal to 0, contact is just about to slip, means it just about to end. If n is less than 0, there is no contact between them. Easy. And conservation of momentum. If F net is 0, then delta P is 0. Pf minus Pi is 0. That means Pf is equal to Pi. Final momentum is equal to initial momentum. That means momentum remains constant. From here we get if F net is equal to 0, delta P is equal to 0 and P is constant. Now coming to the spring force. It is based on Hooke's law. Hooke's law is nothing but Fsb is equal to minus k delta x. I'll explain this in detail. Fsp is nothing but the spring force. Force applied by the spring. It is a variable force. Minus k delta x. Minus it gives us information that it is opposite to the direction of force acting on it. It does not give any It just says us direction, not a magnitude, as force is magnitude as well as direction. Negative sign implies the opposite direction to elongation or compression. K is spring constant. It is different for different springs. And delta X, net elongation or compression in the spring. Let us take few examples to get the concept clearer. This is attached to one and which is fixed. X1, this is elongation. This spring has been elongated x1 units from its natural length. Then we get FSP is equal to Kx1. This is not FSP, this is actually magnitude of FSP. Coming to the direction, force is acted in this direction. So spring force would be acting opposite to that. That is in this direction. In the similarly, if two forces are acting on opposite direction, these two are leading in elongation of the spring. That means magnitude of spring force is equal to K into x1 plus x2. Spring force in a massless spring is same throughout. It has same spring force here and here and here, anywhere in the spring, if the spring is massless. In our syllabus, we consider spring as massless. And K is inversely proportional to L. K is nothing but spring constant, L is length of the spring. We'll get clarity by these examples. Okay, we'll take a spring of length L and spring constant K. If we break it into two equal halves, then it would be the spring constant would be doubled. As the length is half, then spring constant would be doubled. It is inversely proportional, right? And K also determines the strength of the spring. If a spring has more K, spring constant, then it can be compressed or elongated more. Combination of springs. If a spring of K1 and K2 are attached like this, then it is equivalent to a spring of spring constant K, where 1 by K is equal to 1 by K1 plus 1 by K2. By taking an LCM and adding up, we get K1 plus K2 by K1 K2. If we find two springs parallel to, then we can take one spring instead of the both like this with spring constant K, where K is equal to K1 plus K2. Okay, in the next video, I am going to discuss about friction and some other points from Newton's laws of motion. Thank you.